Hello, my name is Vladimir, and I'll be presenting my video for the assignment about recurrence relation and proof by induction. So the exercise is regarding this function h of n, which is the number of hexagons needed to form a pentagon with n hexagons on each side, such as in the image. And our goal is to describe and explain recurrence relations to express h of n, and use the proof by induction to prove that h of n 5 over 2 n plus 1 n minus 1 is a correct closed form solution to our h of n uh, recurrence relation for all valid values of n. So the way I approached the problem was to first count the amount of hexagons that each of the pentagons had. So here we can say that for the first, let's say, row, because we see that there's only like one line of pentagons, which is like for three-sided, like three hexagons per side pentagon. We can count a number of 10 hexagons. Then for the other one, it's 10, which is the first, again, a smaller pentagon plus 15, which is the other one. I count them by hand. And then the last one is the same, where we're adding like the first one plus the second one plus 20. So after looking at the relationship, we can see that there's like a five multiplier of 5 that's being added every new addition of a row. And so after doing a little bit of testing, I found out that the recurrence equation would be the following, which is h of n. It's 10 for if n is equal to 3. And after, when we start growing on numbers, it would be h of n minus 1, which would be like the previous function, the value of the previous number, plus 5 multiplied by n minus 1. So for example, here if we have n equals to 4, it would be h of 3, which is 10, plus 5 by, again, 3, which is 15. So it's 10 plus 15, a little bit like here, like we saw here. And then the same as going on forward. So then for the second part of the exercise, which is a little bit harder, we have this function, which is h like a let's call it lower cap h of n. It's equal to 5 over 2 by 9 plus 1 by 9 minus 2. And we have to prove that it's a correct closed form solution to h of n, which is the following for all valid values of n. So for the first case, which is the base case, we just replace the n value by 3, and we can find that it's equal to 10. And then I did a little table on the side just to represent the following 5 values after the base case, which is 3, and they all fit perfectly, so we can say that it's working for at least the 5 first numbers. So then to prove for all of the other numbers after, or to prove that it's a closed form solution for all the values of n, we have to do like an inductive hypothesis, or like a proof by induction. So if one way I understood, assuming that h of uppercase h of k is equal to lowercase h of k, which is the function that we were giving, the equation, 5 over 2 plus k by k plus 1. Yeah, so here we're using n equals k. So k would be like an integer that's bigger than 3. 5 over 2 by n by k plus 1 by k minus 2. Our inductive, this is like the inductive hypothesis, and our inductive stave is to prove that if h uppercase h of k plus 1 equals lowercase h k plus 1, then like we have a closed um, how you call this, a closed form solution to h of n, which means that for any n value, h of k is equal to h of k. Uppercase h of k is equal to lowercase h of k. So what we do is that we replace n by k plus 1 in the h, which finally finishes by being, which is our recurrence relation. We get h of k plus 5k, because if we remember, our recurrence relation is h n minus 1 plus 5 minus n minus 1. So here if we add the k plus 1, we only get like k, and here same. So this is our base, like our equation so far. And then doing some algebraic calculation, which I'm not going to go over, we can find that h of k plus 1 is equal to this, which is the same that we're trying to find, which is the equation that we were giving at the beginning of the exercise. Um, this one. Yeah. So we have proven that it's a correct closed form solution. I was just trying to see if there was a special name for that function, but it seems that it's just what was given. So therefore, h of n plus 1 it's equal to lowercase h of n plus 1, which means that h of n is equal to lowercase h of n. So that's my video. Thank you very much, and hope you have a wonderful day and a great week. Thank you very much, and see you.